Hello, everyone. Thanks for waiting. Setting up lib stuff take a little bit of time. My name is Valentina, and with my teammates Leo and Florencia, we are part of the Spyropoulos studio, where we study the elemental. So basically, we research natural phenomena as a form of technology. But I think that at the core of the studio, we're really trying to do is to think architecture in a very different way. So our thesis sees potential of creating a space that is in continuous formation by harnessing the hidden forces that structure everything around us. So these invisible forces don't make any distinction between solids and liquids, which basically reveals the granular nature of matter. By using these forces, we learn how to influence matter, shaping its behavior, and creating legible spatial patterns that evolve over time. With our first experiments with granular matter, we started to see how by controlling the space between the particles, we could temporarily arrest the state of a matter, and for instance, making solids behave like liquids. And on the other hand, by arresting particles in fluid environments using frequency, we explored the particle-wave duality, where we learned how particles self-organize through wave interference interactions. Here you can see the nature of our research and the curiosity we've had in order to observe the experiments in a way that inspire new questions. And throughout the research, we've been designing environments to observe and control the phenomena. All of our experiments are ephemeral and exist only as long as this is invisible force that influence matter. And throughout the process, we realized that there was this potential for spaces to be dynamically reorganized through the interaction of matter and energy.
Air as infrastructure has been an important idea that has informed a lot of the granular experiments after fluidization. So we looked into how we can influence and displace matter through a choreography of air. This led to us designing controlled systems that help orchestrate this choreography. In one of the prototypes, we programmed 16 solenoids or air outputs to create a sequence of airflow that we wanted. We observed these particle eruptions and these angle of repose formations, and also through digital simulation, we mapped out these particle displacements to better understand the distribution of the particles. We also tried physically to have different arrangements and different angled air outputs to see the different formations. Vector fields were a good way to make legible and design with the seemingly invisible air force that creates the choreography. While air increases the spacing between the particles to make solids behave fluid-like, we also looked in the opposite direction to decrease the spacing between the particles to arrest matter. And by melting salt directly and spraying it on top of the sand formations, we were able to create structural properties with the sand formations. Through numerous iterations, we accumulated in a 2-meter-long model, which suggested possibilities of shelter and occupancy. A key characteristic of this binding method is the sensitivity to moisture. In other words, when it rains, the structure will dissolve back into sand, and the arrested particle will become free particle again. So this offered us the opportunity to think of this as a cyclical formational system, and the interplay between solid and fluid behavior were fascinating to us.
Studying granularity in a fluid environment revealed the wave phenomena. Waves are invisible forces that affect everything around us. They carry energy with them, causing matter to vibrate. We started studying this phenomena through sound waves as frequencies, vibrating a viscous material until the ascending waves became visible in the surface. At different frequencies and fluid depth, a variety of standing wave formations can be observed. Generally, the higher the frequency, the finer and smaller the surface patterning. The studies of wave patterns led us to the wave-particle duality concept. We explored this through the hydrodynamic quantum analog known as the bouncing droplet. In this experiment, a silicone oil bath is vibrated vertically through the use of frequency. We create droplets out of the bath by introducing a sharp object that ejects the particles upwards. Even if both droplet and bath are the same material, when coming down, instead of merging with the bath, the droplet starts to bounce. The particles are now arrested through frequency. The way this bouncing is able to happen is by compressing a thin layer of air underneath the droplet that impulses the droplet upwards. The air in the system is completely renewed with each bounce, and with the change of pressure because of the vibration, it functions as a never-ending limit between the droplet and the bath. What is not always visible, but it's always present, is the wave underneath the droplet. Both particle and wave are in correspondence with each other, meaning the droplet exists because there is a wave underneath itself, and the wave exists because there is a droplet at the center of itself. If the acceleration of the bath is low, the droplet can only bounce in a stationary bouncing regime. When we increase the acceleration, the droplet enters a period of resonance with the bath, and it gets shifted from the center of its own wave. When it comes down, it lands not on the center of the wave, but on its fold. This pushes the droplet to one side and starts walking across the bath. We call these types of droplet walkers, and you can see here a path of a walker over a 15 minutes time lapse on a circular orbit. Complexity quickly emerges when two droplets interact. You can see here an example of how a pair of droplets interact in an orbiting manner, with their behavior being guided by the relationship between their waves. The organizations become more interesting when more droplets are added to the bath. Here, the wave field starts to receive information from multiple sources, and the pattern is dependent on each of them, on their proximity or level of interaction, and on their trajectories. When we have a low frequency, such as 40 Hz, we can get more stable patterns like triangular lattices that are able to hold themselves for a longer period of time. On the other hand, when we have a higher frequency, we can have more droplets organizing into a packing system, although the pattern is more unstable. By mapping these interference patterns, we were able to visualize the relationship between the droplets and their respective waves, providing insight into such a wide variety of behaviors that can occur during that interaction. To be able to do these experiments, we designed a prototype that was able to isolate the control factors and reduce the noise of the system. With this prototype, we were able to create and define all the parameters of what environment means to this system. Now, with a change in the vibrational force, we can precisely control the space between two droplets. We can go from both droplets being completely side by side to creating space between them. The same thing can be done with an aggregation of droplets, although here the wave field starts to have a key role. Because the organization is locked into position, we're not able to reduce all the space between them, but rather create a pulsing behavior by changing the size of the wave through modifying the bath acceleration. We then took the same concept but tried to program it directly into one sound. When we compose a sound out of the combination of two frequencies that are slightly misaligned, we can start to observe the space between the droplets being modified through frequency. And when we have many droplets, these frequencies create a stop-and-go motion. The droplets are able to walk, but then when the misalignment of the wave occurs, they stop for a bit before resuming the walking mode, creating almost like a double state arrestment of the particles.
While we were studying the phenomenon, we also implemented a digital simulation of the phenomenon in which we harnessed as a design tool. The only way that we found to replicate this rich self-organizational behavior of this bouncing droplet system was through a mathematical model. The model itself can be broken down into three different parts. First, the vertical dynamics of the droplet. Second, the wave it creates upon impact. And the horizontal dynamics, which is the trajectory, which is dependent on the slope and gradient of the wave. So first, the vertical dynamics accounts for the gravity force and the impact force upon impact. And the wave is created upon the impact in which interferes with the surrounding wave field, informing a relational behavior between droplets. And multiple droplets can occupy one single wave field. But when there becomes too many droplets in one wave field, the wave becomes so big and steep that the droplets get repelled out and they reorganize. And now looking on plan view, when they reorganize, like in the physical experiments, there are certain configurations that they stabilize into. And the most common one is what's called a lattice structure. It's an equilateral triangle lattice, like so. And by understanding these different configurations they organize into, we tried out different dynamically stable formations, and our attention turned towards the variety of waveforms that's produced from these configurations. So we iteratively added singular droplets to these stable wave formations, and we also created a separate script that would translate these 2D waveforms into 3D. And from this iterative testing, we saw these different waveforms as key frames, and with a choreographed droplet or agent, they could transform from one formation to another. This was one of the initial tests that we did, adding an agent and seeing its choreographed movements to inform this three-dimensional space that is continuously in formation. And looking more carefully at the interaction between the agent and the droplet, there are two different ways in which the agent can actually displace the droplet. The first one is by pulling, going into the wave itself, and going at a particular speed, which is less than 1 meter per second. It can pull not only one, but multiple droplets at a time. And to exit the wave field, it needs to go above 2 meters per second, so just over the walking speed. And the second method of displacing the droplet is actually in that lattice formation, where two agents choreograph in a way that they move forward and push the droplet forward. And the more agents you have, the faster you can move this droplet. Spatially, the simulation can inform a choreography of interactions that bring the person in as an active participant in this space. And yeah.
With the curiosity of what would be the implication of multiple sources of vibration, we scaled up our prototype, which also implied a change in material. We took the studies of the wave phenomenon to water. This new tank consists of 7 transducers arranged beneath a membrane capable of generating distinct points of vibration. To achieve this, we designed our own PCB boards that are capable of generating different frequencies in an analog manner. These boards serve as the function of the control system, and they play a crucial role in the prototype. They allow us to receive data from a sensor that measures a specific environmental aspect, process this data through the board, generate a corresponding frequency, amplify it, and send it back to the transducers. In this way, the system can actively sense its environment and create a distinct response to the specific interaction it's receiving. Our goal with this prototype was to be able to demonstrate its versatility as a proof of concept in various scenarios where it could sense environmental information, such as the aggregation of people in a space, an object close to the water, and then respond analogically by feeding this input into the system.
So after incorporating this digital and analog human interaction, we started to speculate how we could spatialize this phenomenon at the human scale. So in all of our physical experiments, as you've seen, we haven't been directly designing the environment, but we mostly have been creating conditions for an environment to come into being. So in that transition from the molecular to the landscape scale, we started to recognize an opportunity for a new type of environment, for a collective public experience. In that context, an urban park became an interesting testing ground for our system. To give the project a sense of scale, we took the boundaries of Hyde Park to rethink this fluid dynamic park as an adaptive landscape shaped by the relation between matter, wave interference, and human participation. This park reorganizes itself to accommodate different programs into the field, offering an interface to explore the dynamic morphologies that adapt to human occupancy. The local interactions between humans and the wave influence the global wave field and the organizations of the particles. When we started to simulate larger crowds, we saw how the space evolved into much more intricate and multi-center conditions, creating a dynamic choreography of space that remains in continuous formation. As crowds converge, their activity influences the space. So when you have higher crowd density, that will increase also the interference of frequencies, amplifying waves and generating new organizational patterns. These patterns in turn create a variety of spatial functionalities. For instance, if we think of a larger wave that could accommodate an amphitheater, the smaller ripples created by the frequencies of the people can serve as a seating. So this is a system that can operate across multiple scales, adapting to different needs. We see viscosity as a parameter of the material, so taking it as a characteristic that defines the surface tension. So we investigating throughout all the research that you've seen different states of the same matter. We see potentials in materials like non-Newtonian fluids that can solidify, for example, when they get impacted. However, we acknowledge that there are certain limitations, not in the materiality itself, but mostly with the way we engage with matter. So we started to think about tools that would allow us to demonstrate these ideas in a way that capture that ephemeral, relational, and responsive nature. So first-person experience through VR tool allowed us to experiment what it would be like to be in this space, a space that would challenge our understanding of permanence, focusing much more in the spatial logic that we have uncovered throughout all research. So navigating the environment by extracting information from the way actually offers a very novel way of experimenting and understanding the space. Because also in the VR tool, we can alter the scale of the person. And for instance, if we shrink the scales, it can be immersed in the wave field. But when you can get expanded, it will enable you to perceive the broader logic of space. So this space, we think that it aligns with a world that is in constant motion. It is a space that not to be passively observed, but one to be actively experienced and shaped collectively. The intuitive information embedded within the field guides the participation, allowing people to influence their surroundings. And if you allow me, I will read our last concluding comment, because this is that envisions architecture as a continuous formation, where space is created through a choreography of forces and matter, open to time and shaped by the interference. It offers the possibility of rethinking space as an intricate relationship of horizontal fields conditions, a framework that invites collective engagement and dynamic transformation. What emerges is a novel or a different spatial paradigm, a relational, evolving, and participatory system that redefines how we inhabit space. Our work hasn't finished. It keeps inspiring new questions for us. In this continuous research to demonstrate how a fundamental understanding of matter and energy can inform a new materiality, reality, and built environment. Thank you for your attention.
And to conclude, I will walk you through a bit of our prototypes and models. This first one over here is our sand solidification model. So the idea of this prototype was to be able to demonstrate how we can temporarily arrest one of the formations that we were creating with sand. So it's a temporary arrestment of a choreography of matter. The second one over here that's playing is the bouncing droplet experiment. It's the prototype that we perfected to be able to isolate all the noise of the environment, to be able to create these bouncing droplets. Right now it's playing with the Faraday waves. That's another thing that we studied. And the way it works, it has a piezoelectric droplet generator. It has a leveled base that isolates all the vibrations and misalignments of the tables that we can get. And it also has accelerometers to measure if the vibration is being equal on all the plate. This one over here is our final tank that we were showing. Right now is vibrating at a low frequency. It has a set of sensors that in this case we design over the table, so I could turn it on, and although it has half the level of water, we can turn this off. I can turn it on in order to be able to use the sensors as input information for the tank. So in this way, we can now use the sensors to create a response. And the response depends on the height of my hand as well. And well, this is the control system for this tank. That is all the PCB boards that we made ourselves to be able to read the information from the sensor, process it, generate the weight according to the distance and the frequencies that we set, and be able to send it to the transducers that are underneath the tank to vibrate. And this last over here is our sand prototype with the control system of the 16 solenoid boards. I can also turn this on to see some of the studies that we were looking into with the sand. This is just a little bit of fluidization of the sand and patterning on the surface. And it all works based on this control system that we have over here. And going back over there to Vale, we will show you the VR as a last prototype or experiment.
Just whoever who's curious to test our prototype while we receive the critic is invited to join Evelyn, our phase 1 helper. She will guide you through the experience. Thank you.
Start?
Yeah.
Okay, so I am absolutely fascinated by this work. I think it's incredible, and so precise and so thorough and so consistent, and at the same time experimental to the core, that I think is wonder. It puzzles me, the idea of having a state, a physical space that is in constant build-up or in a constant process of being formed, and that is what a desert is anyway. And we are very familiar with the context of a desert. And because the temporality is not so let's say, fast as you have presented in your animation or simulation. But it is what it is, and it is exactly that. So if to think of the capacity that we have to, via sensors and via, let's say, engineered systems to be able to shape it, I think it does, it's an incredible promise for public space. Especially, I can imagine playground environments and more, because in those kind of environments, you more and more you are seeing that more, let's say, contemporary playgrounds are also looking at how can they bring back the adults into the playgrounds, because the playground becomes a social space, it's a place of relation. And I think that through your system, there could be the possibility to shape certain experiences that would call in for this collective, more social behavior. So I think it has an incredible power. And maybe the last comment I want to make is that there is a relationship between energy and matter, because in some ways we need a lot of energy to shape this matter, but maybe the shaping of the matter could be creating energy too. So almost like a perpetual mobile situation. I don't know, but for me it calls for a lot of imagination in what is possible in this space between technology and matter. So fantastic.
I will follow this this discussion. Thank you so much. First, because I think this kind of project is very important for academia, because this is a difficult situation in architecture, and you combine three things, which is very important for me. First, strictly you are connected with architecture discipline. Next, you use experiment, but that kind of experiment which are very close to art. Because when we see all the models, it is not about the technology to produce space in between. It is artistic models. We enjoy in models as such because this model can be architecture also. So for me, my impression is thank you for combining analog and digital, not only in models, but in your thinking. There is huge topic, what is space? What is space in between? In architectural theory, we don't have any strict theory of the space. We can discuss what is space, and no one in this room can explain what is space. But you offer some kind of definition that space exists only in movement, in motion, and it is very true these days in architecture. So thank you very much to show that space can be only visible in movement. I have only one remarks considering animation. I think that you didn't have time at the end to produce more fragile animation, which is completely in your philosophical field, because I had in my mind all the time Spinoza from theory and philosophy, Peter Eisenman, concept of folding, smooth space, etc., etc. So I think that you can think how can you use result of your research. It is not just experiment. It is very, very good, very deeply focused search connected with architectural field. So thank you very much for this kind of experiment in architecture.
This is why the AA is the best school of architecture in the world. It's exactly what the school has always been about. It's about reminding us of the magics that are around us and which are all exploitable. We spend our time trying to articulate space and form, and here in front of us is a way of exploiting space and form. It's beautiful, stunning. It's been around for millions of years. We're just beginning to explore it, and you're exploring it beautifully for us. It's magic. I think there's enormous scope, and as a participatory system with human beings, I could imagine all sorts of amazing ways of creating it. Fantastic work.
I mean, I want to add to that just the fact that, I don't know if everybody has seen how beautiful you have built the actually control elements and the circuit. You made the circuit boards. You designed. I mean, the fact that you also treat every piece like an art piece is very feels very beautiful. But to the effect, I couldn't help to think that what would happen if we combine your last project with your project, right? And create or lean on physics to create virtual environments, and you tested a bunch of options, right? But I think there's a massive potential to create some sort of sense of, in a way, I think what virtual environments struggle with at the moment is that it's difficult to ground our mind in the virtual reality. What I mean is that if you're in a space that you perceive as unpleasant or ugly, then your mind is less grounded and you're less present in that space. And the moment that there's some familiarity or something that you enjoy and there's a connection made, I think what I'm trying to say is I think there's a really interesting thing to explore about how we translate material physics in the virtual world to create a sense of belonging or a way to stabilize my experience in the virtual world. So I think it's very inspiring and beautiful, your work.
I think I see it like this as well. And it's not only a sense of grounding, but these are organizations and organizational patterns, even in a static condition. They're interesting because they have multiple degrees of overlap and interpenetration of domains and degrees of fuzzy logic intricacies of organizational articulation. And I think these this interpretation is great, and it's a first step, and you took one of your systems. This could easily have zones where the particles or sand flows, and there's another formation very beautifully of the blowing coming in, droplets, etc., as well as static zones where the things blow over. So there's a lot in here to exploit. This is probably the quick and first sketch. It's interesting. But if you get wood in the scale of that it becomes monotonous at that scale. And the idea of a park initially of a social interaction space, which is very playful and open. I wouldn't call it a playground because it would probably we still have purposes there of hosting an event, of hanging out, of meeting people, etc. So yeah, I think I agree with your interpretation. I could also see to think some of this could even be physically implemented in a park landscape. These very kind of shallow water pools which you have in parks. You have fountains. Maybe you can walk on this. Maybe there's vibration. I don't know about sand. Might be get into your nose, etc. But we have these clubs where you have these kind of ball pits and so on. I mean, I could also see a physical version of this. I wouldn't make it too much playground and playful. It should maybe transport some purposes, not just relaxation. But I think that's a great leap, and bringing in the crowds. And then the question is, how much are the crowds active? How are they responsive? That kind of loops and feedback loops between individual crowds and the formation hasn't been a lot articulated, but this could exist, of course, first in the metaverse, because that's where you can run right now, and then but I also always think that some of the things we explore in the metaverse will feed back into the physical environments, and which we've been thinking of dynamizing those for many years, using light. By the way, light is another medium which is very important here, because when some of these ripples effect, we start to see them only when the light hits it flat, or also when the drops jump and suddenly the light catches them. So that phenomenology, it's not only organization, it's also phenomenology. And in the end, once you use has human occupation and these things start to mean something, then semiology comes in as well. But yeah, I'm also fascinated, and I'm very happy that you brought it home into architecture with these last attempts of interpretation.
It's a tremendous amount of fun to watch, but I think what I've really enjoyed is actually most of the things that you're dealing with also leave no trace. So as much as this can be physical, it doesn't demand a physical manifestation or output, which brings it into a much more philosophical, not to bring the missing partner of your pairing. In that, actually, there's an ambiguity in that a lot of the studies are about the droplet of water sitting on water, and then you end up with the human sitting on a surface. And I'm assuming that there's an inference that it's a sort of matter and energy question. And then that starts to hint at something around the formation of community. So the mathematical formation of community when it comes to the water droplets, the formation of community is left as an open-ended question as it interacts with energy in terms of a human community in public space. And I quite like that it maintains its ambiguity as a kind of analogical relationship with something that's deep in physics, but also has an inferred relationship to a kind of a future social agenda. But I like that there's no answer, and maybe it has to stay that way. So that much I very much enjoyed. Fantastic presentation.
Yeah, a lot has been said. I mean, that's why it's called DRL. Amazing. I mean, it's a combination of science and design. I think there's a huge potential when we think about the future, what public space is in terms of smart city concepts. The future public space might be totally different. It's not going to be, there's less traffic, electric cars. There might be new concepts of public space. And I think, your concept could be very important for connecting towards these new systems. So well done. It's amazing.
Maybe I shouldn't have the microphone at the end. David already told me that if you're the tutor, you shouldn't speak. So I think the only thing that I would say is that maybe the things outside from what has been said that I appreciate about your project is more about the spirit of exploration, like just trying things, see what you learn from them, be curious, try to instill a rigor. And control here, even with all these control systems, is an illusion. What I really find quite provocative about the project kind of goes to Marta's point about these things look very familiar, like a dunescape, like a this, like a that. And the reality is that that's all aspects of our world are always changing. We're just not perceiving those changes. So even that slight change of the everyday, I think it's like watching the clouds pass you by kind of thing, those kind of very nostalgic, arty kind of things that you see in cinema. In some ways, I think here speak to something I think very directly. I do think public space is an important thing to reinvest some energy into, because it's a term that means a lot to me, but to be honest with you, what that generally means to most people is just to have open space. No definition, left over. And it used to be a space of activity, of riot, of protest, of celebration. I mean, this is what public actually meant. So I think this kind of speculation, I think, is important. And I think even seeing it more like when Patrick says that light is very important, you focus a lot on the surface of whatever this viscous material is, but all of its atmospheric attributes, like you mentioned air for the bouncing droplet, but it's also refractions off of the liquid, and all of those things I think start to construct the architectural qualities of this. And I think the more that you allow yourself to just appreciate that, I think the more you will take it away from art and into the domain of architecture. When I first saw you guys put the light on this, it reminded me of a piece of Rebecca Horn, which is a pool with one kind of kinetic just coupling, right? And the surface tension of that made a very beautiful refraction. When I see the potential of people actually interfacing this, that whole idea that was in this space about constructing novelty, like Gordon Pask and Price and all of the people here in the 60s, 70s, and 80s who had this dream about this kind of stuff, how to sustain novelty, how to build that into different ways of thinking about interaction, I think is important. So I'm not sure if it's a playground, but I think the act of thinking of this as serious play is an important part, I think, to conceptualize how you work on projects like this. And I think you guys have always entertained our conversations, I think, in a very spirited way, without really resistance, which I think is also a testimony in the belief that if you work at something, you know, a lot of these kind of things that you're working on are very at hand. They're tangible. And, you know, when Leo pans all of these equations, that always scares the hell out of me with all those post-it notes, because I don't understand them. But we know that it drives a lot of the things that we see in the world. So I think going out, speaking with people like you went, you know, that has value. It's not just a tick box. It's about engaging other disciplines to kind of also help you along the way to think about possibilities. So I think you guys have come a long way, and I think you deserve your accolade today. So thank you so much for that.
Thank you.